He kept his mother's photograph in his wallet and a folded piece of church bulletin from back home that he read when the alarms were quiet and his fists ached. The plant lived on repetition and interruption. Shift change at midnight brought the chorus of boots and the smell of boiled cabbage from the mess. At 1 a.m., they ran acceptance tests. Engines strapped to test cells, propellers choked with blankets to muffle the roar, instruments recording vibration and oil pressure. Some nights the test sang, steady needles, even temperatures, the shallow, confident rumble of a heart set right. Other nights the test cells barked and then exploded into problems. Bearings scorched, cowlings that warped, rivets that walked themselves loose when landing loads arrived. Each failure was a small betrayal, each success a temporary truce with physics. The first failure that settled into their bones was a lesson in geometry and heat. Fuselage skins, stamped from sheets meant to be thin and uniform, began to cup when riveted. Under the hot flashes of welding torches and the compression of the rivet gun, flat surfaces bowed into shallow domes. At first, the defect was cosmetic, dismissed as fit and finish. But when a cowl panel did not mate cleanly with its frame during a test assembly, a hairline gap let in air currents that upset cooling flow and gave an engine a fever. The aircraft in the test cell would run lean in one sector and flood in another. Gauges jittered, then tumbled. Iteration 1. The team tightened tolerances and retooled dies. Harold Wentworth, a young draftsman with a hand that trembled when he sketched and an idea for an extra datum hole on the skin, argued for a new jig to clamp parts during riveting. The jig held the panel across a greater area, reducing cup formation while the rivet set. The floor fabricators built the jig from leftover channel and angle in a matter of hours and bolted it to a bench. For a week, the line breathed easier. The panels sat truer. Acceptance runs haltingly improved. Then, one humid afternoon, another failure surfaced. The rivets themselves failed under cyclical vibration. They did not shear, they crept. Their heads developed micro-cracks and, over the course of carrier landings simulated by shakers, loosened until whole panels whispered. A maintenance crew discovered a hairline fracture in a primary spar access plate during a routine inspection, a crack that sent a shiver through the plant as if someone had loosened an anchor. Iteration 2. Metallurgy and fasteners came together in a long, ugly meeting. Brackett argued that heat treatment on the rivets had been uneven. The tempering ovens had been pushed to capacity, their atmosphere fluctuating under the demand for accelerated schedules. He proposed a change, a longer temper cycle at a slightly lower temperature to refine the grain structure of the rivet heads, making them less prone to brittle fracture.
The furnaces were old and temperamental. Adjusting their cycles required tinkering with thermostats that had been replaced a dozen times, and a shift of reluctant operators who trusted the rhythm of what they knew. They changed the cycle, marked rivet boxes by lot, and began to track failures by batch. It worked for a while. The cracks were fewer. Sam marveled at the change, at how a slow touch in a furnace could quiet a problem that had felt mechanical and inevitable. But the war had a terrible appetite for unexpected consequences. The altered rivets, when combined with a new adhesive used by another plant for a cockpit seal, created a corrosion cell where moisture pooled unseen. Months later, in salt spray tests, panels showed pitting around rivet heads. The team had fixed one thing and, in doing so, summoned a new puzzle. Human life threaded through each technical problem. Robert Kane, a fitter who had been with the plant for 10 years and who could name the birth weight of his children in inches of steel, lost a thumb in a press accident during a frantic rework shift. The press had an old guard that stuck. A part that should trip and stop the die had been overridden because the line couldn't afford another stoppage. The accident silenced the bay. Men and women gathered at the infirmary. There were proper apologies later, official forms, and the slow legalese of compensation, but in the moment, the plant's pulse diminished. Robert came back on light duty, his hand in a white plaster cast that he signed for good luck with a stub of pencil. "Bob, don't let me down." Robert's cast became talismanic. Men traced their fingers along the chalk scrawls on the walls, names and wins and grievances, like people who touch the hull of a ship before they leave harbor. For the assemblers, the cast represented a cost that no efficiency metric could quantify. For Brackett, it was a rebuke and reminder. The tempering cycles and the new jigs mattered not only to the airplane, but to the men whose fingers cut the strops. The third set of failures was less dramatic, but perhaps crueler for being incremental. Cooling. The Hellcat's power plant demanded temperate air across its cowling. In laboratory runs, engines chewed through power with polite, predictable appetite. But on carrier decks, with the sea washing heat back into the intake, temperatures rose. The cowling vents, designed for a certain flow, choked in salt-laden air and low-speed taxi operations. Test flights returned with elevated cylinder head temperatures, and pilots radioed that the engine needed richer mixtures at times that didn't make sense. In one acceptance trial, a flight engineer noted a persistent hotspot on the starboard side of the engine compartment, localized heating that no one could initially explain. Iteration 3. The draftsman, led by Harold, suggested a reworked baffle scheme, subtle reshaping of internal flanges to direct airflow where it was most needed.
They conceived a deflector, a small curved plate that would nudge air across the hottest cylinder rows. It was crude at first, stamped from scrap, welded into a mock cowling, and held with cleats. The test rig ran quiet success for a day. Then a gasket blew on a neighboring system, giving the team a sobering reminder of systems integration. Every change tugged at the web. Every fix could strain an adjoining node. Each iteration carried the same anatomy. A failure discovered in a test or on the deck. A tense meeting where men hunched over drawings and part numbers. An experimental modification cobbled and tried. A temporary lull, and then a new problem. The repetition forged them as much as the physical metal did. Calluses of patience, the dull optimism of people who had to believe that tomorrow's run would be the run that held. Through it all, women on the assembly line kept cadence. They handled the delicate shapes of the cockpit frames, coaxed wiring into tight harnesses, and riveted with a patience that was precise enough to be a kind of prayer. At the small sink in the tool crib, a woman named Lillian, gray hair braided at the neck though she was only 30, kept a locket with a photograph of a boy with a cowlick and a shy smile. She would touch the locket in moments when the alarms wailed and the blackouts pulled the light away, as if remembering the small human things might steady her hand against the punishing rhythm of production. Outside, the threat overhead altered even the mechanical rhythm of the plant. Air raid drills came with regularity. Sometimes the alarms were a drum roll and nothing followed. Other nights the plant flashed red and the floor fell silent as men and women ducked into shelters or pressed themselves against machinery to avoid beams of searchlight. Windows were blacked out and skylights covered. Engines and fuel lines were moved and muffled. Work continued in fits and starts, an almost normal production under abnormal restraint. The blackout curtains made the place intimate in a way it had not been intended to be. Faces lit by handheld lamps, the warm halo of welding arcs, breath visible in the cooler pockets of the foundry bay. Those were the moments when the plant felt less like a factory and more like a ship at anchor. Every man and woman a member of the crew, every bolt a life preserver. Small rituals kept the moral intact. Someone pinned a sign in the cafeteria, "Build, not break." It was scrawled in grease pencil, the letters crooked and earnest. A calendar in the office held clipped photographs of pilots who had written back from carriers, notes of thanks in shaky handwriting. One letter read, "Your plane kept me home," and the note was thumbed and dog-eared like a relic. There were funerals for those injured beyond return. There were quiet ceremonies in the plant's chapel for men who would not return from sea. The plant's achievements sat always beside the human toll. Men knew they were forging instruments of war. They understood that making them well could save lives, on carriers, in the air, on tiny atolls, but they also knew that well-made machines served violent ends. Technically, the plant had to marry the urgent with the exacting. Engines pulsed in test cells fitted with stethoscopes and accelerometers. The acceptance regime demanded that each airplane survive a gauntlet of checks before it left the plant. Ground runs, static load tests, harmonic vibration sweeps, carrier compatibility fittings. Each of these checks revealed different truths. A panel might behave perfectly on the bench and misbehave on the flight deck. A propeller that recorded tolerable unbalance on a balancing machine would sing a new note in the wind and create sympathetic vibrations that loosened a control cable. The plant's engineering team learned to look not only at single tests but at sequences, what one failure whispered about the next. Brackett prowled those sequences more than anyone. He carried a slate of problems like a priest might carry prayers. He cataloged each failure in his ledger. The first sign, the ambient conditions, the batch numbers, the operator. He liked to say that metal remembers its making as surely as memory lives in the mind. You can read a part like you read a person, he told Samuel once, tapping a cracked bearing. Look at its face. The grain tells you how it learned to live with heat. The scars tell you what it's been through. Samuel had laughed, a small, nervous sound, then bent his head and studied the bearing as if it might confess. The plant's organizational muscles built around that intimacy. Shift reports became rituals of transfer. Who had seen what? Who had heard a funny noise? Who had a hunch? Engineers and machinists argued late into the night. Brackett's office never locked. People left scribbles on his door, and he, in turn, left comments in margins. Harold sketched a shielded baffle in the margins of a blueprint and left it in the coffee urn. Someone later found it and taped it above a drill press like a prayer. Yet, the interruptions kept coming. Material shortages forced substitutions. Sheets of aluminum arrived with slightly different alloying elements. Heat treatment ovens varied in atmosphere depending on coal supply and operator technique. A supplier's batch of steel had slightly higher sulfur content, one of those impurities that make steel more prone to brittle failure. Brackett, who had spent a lifetime thinking in microstructures, watched his control systems get fuzzier. Every substitution required a new round of qualification. And then there was the test that failed in a way that felt personal. During a routine engine run verification, thermocouples in a test cell began to read an odd transient. Temperatures oscillating not at random, but in a pattern that suggested resonance. At full power, a thin, high-pitched harmonic began and grew like a small animal, feeding on itself until a pressure fitting shook loose. Oil misted, the test shut down, and an investigator swore he heard the part sing before it cracked. Brackett stood under the glow of the test cell panel and listened to the echo of the shutdown. "We're not failing the machine," he told the gathered crew. "We're failing to understand the conversation." He used words like conversation in the manner of someone coaxing discipline from chaos. Over the next 2 days, they set up a series of mock sequences. Engine runs, followed by vibration sweeps, followed by a simulated deck impact. Harold drafted a small foam mock-up of a cow to test airflow anomalies. Samuel bolted accelerometers to ribs and learned to read a trace like a map. They were training their ears and their instruments to hear what the parts had been trying cryptically to say. Not all experiments had a poetic arc. The first prototype of a new baffle warped because the welding changed residual stress on the part. A modified rivet lot behaved better in tensile tests, but showed microvoids under electron imaging that no bench test could have predicted. Tests broke things, they also taught. The plant's culture normalized failure as necessary detritus. Workers kept scrap bins carefully labeled and returned to them often. Each scrap part was a lesson waiting to be deciphered. As the days lengthened into a cycle of trials, another human vignette threaded through the narrative. A young apprentice, Harold, who had once drawn aircraft engines as a boy and now drew them in the margins of official plans, came to Brackett with a sheet of sketches folded into quarters. In those sketches, a simple idea lived: perforated ribs that might relieve localized stress concentrations without adding weight. It was an old trick in a different language, borrowed from boat builders and bicycle makers. Harold had the audacity to bring it to the aeroplane. Brackett squinted at the lines and the names Harold had given to stress points. He asked Harold where the idea came from. Harold said, "My father used it once on a milk cart. We made it lighter and it didn't break." Brackett nodded. He liked practical lore. He liked the way a solution came not from an engineer on a pedestal, but from someone who had seen a problem in a different craft and translated it. They tried Harold's perforated rib in a non-critical spar. The part arrived from the shop with holes sanded smooth and descriptor tags that read like a prayer. Trial 34, Harold. It was a small victory when the rib held under tests that had previously produced stress cracks. It was a victory that did not scale immediately, and so became a lesson in patience. The team had to reconcile how to make a safe licensed aircraft versus a clever trial piece from a shop floor improviser. The regulatory and engineering paperwork that followed the win was as heavy as the rib itself.
Every time the plant reached a temporary understanding with a failure, something else demanded attention. Stricter carrier requirements, a new ordnance configuration that taxed the wing differently, an alloy supplier whose batch was flagged for impurity. These demands arrived like gusts from ocean weather, sudden, bracing, and renewing the conversation about priorities. The plant responded with ingenuity and exhaustion in equal measure. Machines ran longer than they were supposed to. Men slept on benches. A foreman once took his shoes off and left them on a locker shelf because his feet had flipped out of them in the night and he had to run. There was a good kind of stubbornness in the plant, a refusal to accept that a given problem was immutable. That stubbornness created a rhythm of its own. Find, fail, try, brief, tinker, test. Each loop tightened their knowledge. Brackett kept a ledger of runs that read like a novel. Test 12, vibration spike at 3.2 kHz. Test 12A, added damping pad. Test 12B, frequency shift noted, no crack. Over time, patterns emerged. Where once failures seemed random, they began to cluster around certain assemblies or environmental conditions. They learned the voice of the plant. And yet, the human cost shadowed each gain. A pilot wrote back that an engine that had once sputtered had seen him through a night harrowing enough to age him a decade. A widow wrote from a town whose name Brackett did not know and asked simply whether the faces in her son's picture might be remembered. The plant posted her letter on a notice board. Men stood and read it there, slow and mute. It reminded them that each airplane was a ledger of human decisions. Some made in the bright geometry of engineering, some in the gray fatigue of late-night fixes. As morning approached on another long night, the plant received word of a new shift in priorities from the Navy. More planes, faster deliveries. The demand curve did little to care for the temper of metals or the sleep of men. A sense of impending escalation filled the rooms like the smell of ozone before a storm. Brackett went to the foundry, where molten metal hissed as it met the atmosphere of their world. Bright orange rivers pouring into molds, smell of burnt oil and metal traded like a common language. He held a part in his hand that had been made at 3 a.m. and felt its heat cool against his palm. The part was not yet perfect. It had a subtle waviness on its flange, something the die had never produced before and that no one could explain. They were close to a technical breakthrough, the floor whispered about. The kind of breakthrough that arrives not in the neat arc of a film, but as a long, muddy accumulation of small findings.
a revised jig here, a longer tempering cycle there, a baffle that nudged airflow an inch. Each change improved survivability on the deck by a degree or two. The plant had weathered 3 major cycles of failure and had learned.
The men joked sometimes that the plant could take on a storm and still find time to mend a pocket watch. But storms were not purely metaphors. That morning, a distant flash of anti-aircraft fire several kilometers away laced the horizon like a rough bruise. The plant's sirens remained silent, no direct attack was reported, but the mood shifted. Work continued, if only because the plant had no alternative. The line hummed and slipped into its rhythm like a train back onto tracks. Outside, the carrier decks would soon be alive with planes, and somewhere pilots would test whether the machines they trusted matched the trust they had been given. At the end of that long, frail night, Brackett sat on a crate and opened the letter from a sailor that had warmed his pocket. He read aloud to no one the words, a simple confession, "Your plane came home." He looked out a dirty window where the first soldiering light of dawn fought the smoke. He thought of Robert's cast, of Harold's sketches, of Sammy's ears and Lillian's locket. He thought of metal that remembered and people who remembered more. He folded the letter and tucked it into his ledger. He made a small note. Examine transition of stress pattern from pre-rivet to post. Compare to trial 34. Consider perforated ribs. It was work and mourning in the same hand. If you enjoyed deep dives into the machines behind history, subscribe. That morning, the investigations went deeper. The engineers cataloged their failures on a blackboard as if laying out an accusation. Warpage, riveting creep, localized overheating, harmonic resonance, corrosion at fastener heads, material impurity. By noon, the board was a dense fractal map of problems and uncertain fixes. They prioritized by what could cause catastrophic failure in flight, and then by what could be fixed quickly on the line without halting everything. Some fixes were procedural, improved inspection routines, more frequent batch testing, clearer lot labeling. Others demanded experimentation and an appetite for risk. Brackett convened a cross-disciplinary team. He wanted eyes from stress analysis, from the shop, from the flight test squadron that had to sign off on the planes. He wanted a machinist who knew the temper of a press, and a draftsman who could sketch a new baffle in the time it took to drink a cup of coffee. He wanted someone brave enough to ride on a test pilot's report, and patient enough to read a micrograph for grain boundary morphology. They gathered in a small conference room, map of the plant pinned to the wall, a pair of eclipse lamps making islands of light on the table. The meeting was a choreography of expertise, thermal profiles, machining tolerances, supply manifest anomalies. The first tactical move was to isolate failures by sequence. They would not chase every anomaly. They would follow the ones most likely to cascade. They set up a trial cell that could run through sequences: stamping, riveting, heat cycling, flight profile engine runs. If a part survived the sequence without a whisper of distress, it would be green-lighted for scale-up. If not, it would be back to the forge. The plan was simple. Execution, as always, was complex. Late in the afternoon, Samuel stood behind a test rig and watched pointers twitch. He was tired, more tired now than on any other night. But he had begun to learn a curious resilience, that attention could be a kind of armor. He followed a trace that had once been a warning spike and now lay patient and low. He allowed himself a small grin. Nearby, Harold adjusted a mount and told a joke about a patent office clerk who had been fooled by an ugly drawing. Small levity that made the room feel human, but not less intense. Despite these small gains, the plant's supply system flagged another concern: a batch of alloy that the procurement logs marked with asterisks. The asterisks in the ledger meant inspect. The supply man, thin and balding, handed Brackett a sample and said, "We should rerun qualification on this."
Brackett looked at the sample, then at the list of planes scheduled for delivery. Rerunning qualification meant time lost. Time meant fewer planes on carriers. Fewer planes meant more strain on pilots. The ledger began to feel heavier. When they tested the suspect alloy under cyclic loads, it passed basic metrics, but showed a slight reduction in elongation before fracture, one of those small changes that becomes meaningful under shock loads like a carrier landing or a parasite load during bombing. The engineers annotated the result in the ledger: pass, watch in service. It was a compromise that made everyone in the room leave a little more tired. Compromise was not always negligence, but it left a taste as metallic as the plant's air. As dusk gathered again, the shop made a small ritual out of victory, a night run that would use the improved jigs, the adjusted rivet temper cycle, and Harold's perforated ribs. They ran an airframe assembly from stamped skins to an assembled fuselage fitting. They tested the cowl with the mock baffle and ran an engine in the rig for a short, tense hour. The gauges held, the thermocouples slept in steady lines. Where once a hiss had become a threat, the engine sat steady, warm, and obedient. The assembled crew did not cheer. They clapped softly. The applause in the plant was not the noisy triumph of a stage, but the careful acknowledgement of a thing that had been earned in scratches and smoke. Brackett allowed himself a small, private satisfaction. He filed the test results and put a check mark in his ledger. For a night, they had coaxed the machine into submission. But victory in the plant always presaged more hunger. The Navy's demand ticked like a second clock. More hulls, more wings, more engines.
Word came down that carrier squadrons would rotate through schedules faster, leaving less slack for testing. The plant's managers began to discuss scale-up. Can the jigs be duplicated? Can the temper cycles be reliably reproduced on other ovens? Can Harold's perforations be machined at the increased tempo? The questions multiplied. That night, as workers drifted home with grease on their hands and food in brown paper bags, an early warning flared on the horizon. Reports of enemy raids near shipping routes, patrols engaging. The plant's blackout protocols shifted from routine to serious. Men and women checked their tools and bags and then checked their families' names on a list. The air raid risk pressed into the narrative with a sharpened urgency. They were not just producing for a posterity of planes, but for people who would fly in them tonight. The link between plant and pilot narrowed to an immediate line. Inside that narrow line of connection, Brackett found himself thinking of the future in a way he had not before. He pictured the plant silent after the war, benches empty and tools hung like memories on hooks. He pictured a museum plaque and a display of a Hellcat wing hung under soft lights, visitors tracing the rivet lines with reverent fingers. He imagined men like Samuel at 60, folding a son's letter into a ledger and smiling with a memory that mixed pride and the sense of having been part of something larger than themselves. He could not yet see the full arc of how their work would turn history. Only the immediate, repeating shape. Try, fail, learn, and try again. The plant did not sleep. It held a momentary peace that felt more like a held breath. Outside, searchlights blinked across the sky like the careful hands of watchmen. Inside, a squadron of engines now sat ready for final acceptance, their cowls dull under the lamps, their galvanized skin waiting for one more inspection. Every plane on that rack represented dozens of hours of labor, rounded decisions that balanced risk and safety, and a network of human commitments. As the crew closed the late shift, Harold lingered with a small part he had made himself. A rib with the exact pattern of perforations, sanded to smoothness. He wrapped it in a scrap of cloth and tucked it into his locker, then left without fanfare. Samuel stepped out into the coastal chill, his breath a thin cloud. He felt the heavy sense of a night's work behind him, and the lightness of a small, unspoken hope that the next run would be the one that held. The story was not finished. The ledger remained open. Tests would continue. Supply lines would cough and clear. There would be more injuries and more letters, and more midnight victories that were as quiet as prayer. The plant, a place of incandescent labor and nervous ingenuity, had reached a place of tense possibility, poised between petty failures that had become routine, and a breakthrough that, measured in small degrees of trust, might finally let their planes leave the hangar with less fear in their engines. The ledger remained open. Tests would continue. Supply lines would cough and clear. There would be more injuries and more letters and more midnight victories that were as quiet as prayer. The plant, a place of incandescent labor and nervous ingenuity, had reached a place of tense possibility, poised between petty failures that had become routine, and a breakthrough that, measured in small degrees of trust, might finally let their planes leave the hangar with less fear in their engines. When the Navy increased its tempo again, another request for faster delivery, another push to get aircraft aboard carriers rotating through the Pacific, the plant answered in the only language it knew: more hours, more focus, more experiments. But volume alone could not erase the knotted pattern of problems they had traced on the blackboard. Scale-up demanded repeatability. It demanded a way to take Harold's improvised perforations, Brackett's tempering adjustments, and the mock baffle and turn them into procedures other crews could reproduce night after night and week after week. The first task was standardization. The plant's foremen and engineers worked like men trying to teach a hand a new habit. They drafted written instructions, detailed, numbered, and, where possible, illustrated in the crude, direct line drawings that shop hands understood. They took photographs of jigs and fixtures, labeled critical datum points, and color-coded fastener boxes so an operator on the second shift could identify a lot by a glance. The tempering cycles Brackett had pioneered were written into cards that accompanied batches of rivets, a lot number, a time, a target temperature, and a note about furnace atmosphere. The ovens themselves were fitted, where possible, with extra gauges and a spare set of personnel to record actual runs. That work, painfully bureaucratic and achingly precise, was as revolutionary in its way as any inventive burst. The plant had moved from improvisation to process control. The first surprise of scale-up was social. The people who had once stolen moments to tinker now had to surrender some of their improvisational freedom to follow standardized steps. Harold's perforated ribs, once hand-filed and smoothed by the young draftman's own fingers, would soon be produced by a partner shop with automated punch presses.
Harold took it well. Proud, more than possessive, but he stayed close to the die makers, watching tolerances, squinting at the first runs for burrs or slight misalignment. Iteration 4, the die shop revealed a new problem. At the increased rate demanded by the Navy, punched ribs began showing slight offsets as the press beds heated and their beds expanded by a few thousandths of an inch. The offset was small, smaller than the eye could catch, but it was enough, repeated across a rib bay, to concentrate stress at the splice points. Under cyclic load, the splice was vulnerable. Production engineers traced the issue to thermal expansion in the presses and added a simple compensator, a shim set that accounted for bed expansion across production runs and a cooling schedule that allowed the press bed to return to ambient between heavy runs. The fix was mechanical and mundane. It cost hours and one foreman's patience, but it worked. Across the plant, Brackett fought another, less mechanical enemy, record-keeping. With multiple ovens now performing temper cycles in different bays, with rivet lots sourced from varied mills, the need for traceability became urgent. If a batch failed in service, they needed to know where it had come from, who had run it, and under what conditions. Brackett insisted on tags, metal tie tags stamped and attached, notched and placed into a permanent file. He trained his apprentices to read micrographs and to take notes so that years later an investigator could reconstruct the life of a part. More tests followed. Acceptance sequences were lengthened to include not only single tests but chained trials that simulated the life of a carrier plane. Sequence of rivet setting, heat soak, vibration sweep, engine run under simulated deck conditions, then a final shock load. The test rigs grew more elaborate. One night, as winter tried to breathe cold into the plant, a test sequence that had once been a half hour now stretched for 2 days. Men came and went in shifts, monitoring gauges, cross-checking thermocouples, and swapping tea flasks so exhaustion would not seed error. The rig did not always obey. Sensors failed in the middle of a run, and accelerometer's leads frayed and recorded nonsense. The team learned to distrust a single instrument and to triangulate measurements. If 3 gauges agreed, then the reading mattered. All of these interventions fed into a new, more resilient product. A Hellcat that left the plant with standardized rivets, verified perforated ribs, and a cowl whose baffle had been prototyped and then reworked with finer bends and an added shim to mitigate the welding stresses that had warped earlier versions. The plant's technicians documented each modification, and test pilots, volunteer naval aviators attached to the flight test detachment, began to fly the modified planes back to back with older machines to compare behavior.
It was in this phase, when procedures began to harden into habit, that the most dramatic night arrived, one that would be retold in quieter gatherings for decades, half as legend and half as truth. The plant had committed a batch of completed airframes, an entire rack of Hellcats, to a synchronized acceptance operation. The plan was to run the whole series through the new sequence, then deliver as many as possible to a rendezvous point for shipment to the carriers. The sky that night was a bruise. Enemy aircraft had been active along supply lanes. Searchlights kept vigil on the horizon. The plant's blackout curtains were in place. Outside, air raid warnings had been elevated to a practical code. Work went on. Present tense returns as the danger sharpens. A siren keened. Lamps went down to single handheld lights. Men moved with the practiced economy of people who had rehearsed panic. Engines in the test cells idled. Gauges glowed like the eyes of wary animals. Then, the unexpected. From offshore came a line of tracer fire, and the night burst into a low, distant thunder. Searchlights stalked the sky. The plant's roof vibrated with the passing of anti-aircraft bursts. Men hurried into shelters, then out again as word came by telephone. No direct strike, but the raid had been too close for comfort. Under that charged sky, the plant's acceptance run proceeded. The first plane in the sequence taxis to the makeshift ramp and runs. The engine warms with familiar coughs, then settles into the steady, throaty rumble of a well-tuned radio. The test pilot, a stoic lieutenant who had learned to flinch only in the air, clips in, circles the field, and takes off into the blackout-sheathed sky. He has not gone long. The pilot radios back after a short hop. The plane feels solid. The engine holds temperature. The vibrations that had haunted previous models are absent or reduced. In the assembly bay, a hush falls. It is not celebration. It is the measured intake of breath that comes when a danger has been skirted and found to be a shade less deadly than yesterday. Pilot reports flow in the following hour like a chain of careful signals. The plane that had been the object of their tests returns with notes on a smoother throttle response and an absence of the persistent hotspot on the starboard side that had stubbornly resisted previous fixes. The flight engineer's log shows lower head temperatures by a small margin, enough to matter on a long sortie where a 1% improvement can be the difference between a pilot bailing out and finding a safe deck. Verify. The specific thermal improvements and their operational effects require archival confirmation. Avoid citing numerical claims without historian verification. That success, slow and piecemeal as it was, had the effect of permission. The plant's managers authorized the duplication of the jigs. Rivet lots were labeled and released. The perforated ribs were allowed for non-critical spar locations across the next batch of builds. Most importantly, the acceptance flow, the chain sequence of tests, was adopted as the standard operating procedure for all plants in the consortium that supplied Hellcats. What had been a local adaptation began, through formal documentation and a certain managerial impatience, to spread outward. Scale-up produced new problems, because larger scale amplifies subtle flaws. The partner shops producing ribs could not replicate the exact grinding technique Harold had used, file strokes that left a certain sheen on hole edges that reduced crack initiation. The first 100 ribs returned with hairline scores where the punch misfed. The plant instituted a secondary finishing operation, a dedicated bench where lapidary hands smoothed edges and dressed burrs. It was tedious work, and for a while the bottleneck shifted from stamping to finish. Iteration 5, a supply chain friction point. The finishing bench slowed output. Management considered outsourcing the operation to a subcontractor but balked at the risk. Instead, they improvised a shift rotation that dedicated more hands to finishing for a month until the presses could be further refined. The compromise cost time, but preserved the integrity of the ribs. In that one decision, keep the work close, accept a short-term throughput hit, the plant affirmed a principle. Sometimes quality required the sacrifice of speed. The ramp-up was not an unbroken climb. There were nights when more parts failed the chained acceptance sequence, when rivet boxes had to be quarantined, when a whole feeder line was stopped to investigate a misalignment on a fixture. Those nights tested the team's resolve. They kept the ledger honest, and they learned to accept that industrial performance in wartime was a calculus, a balance between risk, speed, and the crew who would fly and maintain the machines. One of the human elements that had been easy to undercount in nights of technical fuss was the compression of fear and pride into small rituals. Robert Kine, whose thumb had been lost to a press, became an unofficial mentor on safety. His cast, exchanged for a leather prosthetic later, bore a carved initial, the K of a man who wanted to ensure no one else paid the price he had paid. He spent mornings at the press bays teaching guards and watching for operator fatigue. He developed a joke-free patience that made him stern and beloved. He would tap a schematic in a meeting and say simply, "If it's worth doing, it's worth staying alive to see it done right." The line learned to respect his presence. Lillian, with her locket and quiet hands, became the last quality check in some sense. She handled delicate cockpit fittings and wire harnesses with a care that inspection forms could not quantify. Pilots who later wrote to the plant would sometimes single out a line worker with a nickname, praising the snugness of a panel or the feel of a switch. Small things that, accumulated, made flight safer. Those letters were pasted up in the cafeteria like prayers pinned to a shrine. The plant's output increased. Planes left by the ton and crated, routed to staging yards and loaded onto ships. There were still defects found in service. Maintenance crews reported issues that demanded recall, and occasionally a plane returned with a structural problem that forced a deeper investigation. But the pattern had shifted. Where once failures were frequent enough to be expected, now they were anomalies to be tracked and learned from. The Hellcats that left the plant now carried the signatures of 1,000 small improvements. The most visceral measure of success came not as numbers but as stories. A pilot, one of the first to fly the new standard machines off a carrier at dawn, wrote a short note and sent it back to the plant. He said the plane handled carrier landings with a steadiness that had saved him from a hard deck that might otherwise have bucked a fuselage. He added, in a line that made Brackett fold it twice and tuck it into his ledger, that he could not tell whether the improved harmony of the machine had been engineering or the hands that built it. Either way, he thanked them. Men and women who had labored under the plant's roof read that note and allowed themselves a long, exhaled relief. Even as the plant celebrated its hard-earned sequence of gains, the reality of war remained a blunt backdrop. Bombing raids near shipping lanes continued, sometimes cutting supply and other times pausing in coastal sectors. A convoy returning with parts from a supplier was hit, its manifest lost or delayed. A shipment of specialty fasteners took weeks to reroute, forcing the plant to reprovision with a close substitute and then to rerun qualification tests. That contingency work cost hours and patience. The plant learned to keep alternate suppliers and to treat contingency as a constant variable rather than an exception. And there were nights when the moral weight of their production pressed hardest. Men read dispatches of raids and losses and felt the paradox of their labor. Their hands fashioned machines that kept friends alive and kept enemies under assault. In the plant's chapel, a small group would sometimes gather, not to celebrate victory, but to pray for mercy. The strange word in a place that built instruments of war. Brackett, who had been known for his ledger and his eye, would sit in the back and not speak. He kept the sailor's letter in his coat and placed it before him like a talisman.
The breakthrough that finally felt like something more than local resolution was less a single flash and more the accumulation of those many, many loops of improvement. Perforated ribs now precisely machined and deburred, a controlled tempering protocol replicated across ovens, a refined baffle design that directed airflow without compromising neighboring systems, and an acceptance flow that tested parts in sequence rather than singly. When the plant reached that state, its output was steadier. The machines it sent to sea had fewer idiosyncratic hotspots and less propensity for vibrational creep. The difference was subtle but consequential. Pilots and maintainers reported fewer emergency recoveries for the particular distress modes that had once been common. Verify the specific causal links between these plant-level changes and carrier operational statistics are complex and require archival study. Any direct attribution of carrier survival rates to the plant's modifications must be substantiated by historical documents. The culmination came in a series of coordinated deliveries. A squadron of Hellcats, assembled under the new regimen, was shipped to a carrier group on a brief window of calm seas. The plant's managers and the test squadron celebrated privately that night with quiet toasts and an exchange of cigarette tins. They did not claim victory over the war. They could not carry that arrogance, but they allowed themselves a measure of pride in a job better done. One of the pilots who had tested their planes returned to the plant for a day and walked the bays, touching a wing with a calloused finger. He found Harold at his bench and said, "Kid, that rib felt like the plane tightened up around me." Harold, who had learned to be less hush about small victories, smiled with the naive delight of someone who had helped make a thing he loved more reliable. Yet, even in the glow of those smaller triumphs, the plant insisted on caution. They continued to catalog their failures as carefully as their successes. They met weekly to debate the next round of improvements and to persist in the habit of not believing in final answers. The ledger grew heavy with notes, fields of marginalia that would, years later, make for telling archival study. War does not unfold as clean arcs. Machines and men tested each other in messy ways. For every plane that returned with the quiet confidence of improved hardware, there were others that did not come back at all. The plant's notice board curated those losses with the same care as a registry of done work. Names of pilots whose planes were lost, scrapbooks of metal, and photographs of men who had written home. A local paper printed a sparse column on the plant's contributions, and the plant's floor hands tore it into pieces and pasted their own snippets beside it. A small, tattered photo of a pilot's wedding day, a scrap of sandpaper, a note of thanks from a mother. Time, the plant's relentless companion, kept moving. As the war wound down, falteringly, and then with a swiftness that surprised even those who had hoped for it, the rhythm of work changed. Requests for planes eased. The supply chains that had once been strained began to reroute to peacetime production. The foundries cooled. Men who had slept on cots began to return to homes or to find new civilian work. Harold took a job in a civilian aircraft company. Samuel stayed, becoming a foreman who taught apprentices what he had learned the hard way. Brackett, whose identity was entwined with furnaces and ledgers, accepted a quieter role as a consultant and mentor, his slate of problems transcribed into procedural guidelines that other plants could use. The plant itself changed slowly. Where once blackout curtains hung and sirens had set a fearful tempo, now the windows were unshuttered, and natural light returned like a permission slip. The machines that had run at war pace cooled and then took on different assignments. Machinery repurposed for peacetime goods in factories that would, in time, invent the engines and turbines of post-war flight. Verify, the specific technological lineage from wartime Hellcat manufacturing to post-war jet and turbine industries is plausible and documented in some cases. Specific claims about the plant's direct involvement in later developments require archival confirmation. Memory, however, outlives production schedules. In the months and years after the war, as veterans returned and communities rebuilt, the plant became a repository of stories. Former workers would come back on certain anniversaries to stand under the rafters and listen for a noise that was not there anymore: the steady mechanical heartbeat of rivet guns. The building itself took on layered meanings. For some, the site of pride; for others, a map of scars and losses. A museum curator, working with a small group of former employees, arranged an exhibit of a Hellcat wing. They hung one of the perforated ribs in a display case. Nearby, under glass, lay Robert Kane's carved prosthetic thumb, a letter from the pilot who had owed his life to a plane, and Lillian's locket. Brackett, older now, came to the museum on its opening day. He walked slowly along the display and paused where the rib hung. He touched the glass as if he might feel the memory through it. He asked the curator for a minute alone. In a small, private act, he pressed the sailor's letter against the case, printed, not the original, and then left without a speech. The museum was a place where noisy factories were translated into hushed artifacts, a transformation Brackett found both comforting and strange. Here, machines became relics. The roar of a test cell became a recorded audio track behind a quiet plaque. The men and women who had walked the line found themselves in donation photographs and explanatory placards. Tour groups read about wartime production and the F6F Hellcat's role in the Pacific Air War.
Some visitors stood and listened to oral histories, the scratchy recordings of pilots and machinists recalling nights under blackout curtains. That day, Brackett encountered Samuel near the exit. Samuel had married and raised a family and kept a small toolbox in the garage. They embraced briefly in the museum's hallway, two men whose lives had been soldered together by late-night fixes and the hush of test runs. Samuel held in his hand a small scrap of metal, the first rivet he had ever set as an apprentice. It was polished by use and habit. He had kept it all those years. He put it on the edge of the display case for a moment, and Brackett nodded as if the gesture was a benediction. Old men and women at reunions spoke of moral complexity as naturally as they spoke of rivets and dies. They acknowledged that their work had enabled destruction as well as survival, and that the judgment of that trade belonged not to any single man or workshop, but to a broader political and historical narrative. Some veterans carried a heavier burden of regret. Others upheld their work as necessary. The plant's story, when told in the quieter voices that came decades later, settled into an uneasy honesty. Craftsmen had oiled and hammered and measured with the intention of making things that kept their neighbors alive, and those same things had been used to wage war. There was also an unambiguous legacy of technique.
The careful tempering protocols, the method of chained acceptance testing, and the attention to finish, a small but decisive finishing bench, became practices taught in post-war engineering schools and industry apprenticeships. Young engineers learned to regard failure as data and to design processes that made quality repeatable. Harold's perforated rib became a footnote in some technical papers, where an old shop floor trick had been adapted to aviation stress relief. Brackett's ledger found its way into an engineering archive box, where scholars years later would pore over the marginalia with the same curiosity he had brought to micrographs. Yet the plant's most intimate legacy was human, the shared phrase that lingered in the mouths of men and women who had labored there. They called it listening to metal. It referred to the practice of learning to read a part's life by its feel, its sound, the microscopic lines etched on a fracture surface. That phrase became a metaphor for a broader humility, an engineering ethic that acknowledged material limits and treated improvisation as the sibling of caution. In quiet moments, Brackett reflected on the paradox that had defined their work. The furnace that gave shape to a wing was both a shelter and a tool of war. The perforations that allowed a spar to breathe under stress were small acts of mercy, but served machines that could deliver violence. He believed, as he had always believed, that the integrity with which one made a thing mattered morally as well as practically.
To make a plane with care was, in his view, to reduce the odds of catastrophic failure for the men who would fly it. That belief never erased the moral complexities of war, but it gave those who labored there a grounding. Years later, at a reunion of plant workers held in a modest hall near the former factory site, Samuel stood and told a small story. He spoke of a night when the plant had been quiet and the cold had settled into the steel. He had found Harold in the die shop, alone, polishing an extra rib. Harold had not wanted to let any burr go unchecked. Samuel said that he thought then that those small acts, of smoothing an edge, of stenciling a tag, were acts of faith. The room listened and then applauded, not for the technical content of his story, but for the implicit truth in it. Craftsmanship mattered. The reunion was not a crusade of celebration. They remembered the injured and the lost. They read the names and observed a silence that felt like a communal accounting. They told jokes and bickered about machine settings, and then, in quieter circles, traded the mail they had never cast. The letters from pilots, the photographs that had been tucked into wallets. Lillian's locket was opened on a table, and the picture inside shown to old friends who had seen the boy before his hair turned white. Robert's prosthetic thumb was reverently passed around like an artifact of sacrifice and ingenuity. As the event wound down, Brackett stepped outside for air. He stood under the old sky and looked across the empty lot where the plant had once hummed. The structures remained in part, silos and a skeleton of a gantry, and the lot had that peculiar stillness of places that once bristled with industry. Brackett touched his ledger's cover, worn and soft, and felt the weight of memory. He thought of the ledger's loose pages, each a testimony to attempts made and sometimes failed, and of a sailor's simple phrase, "Your plane came home." In the end, the story of the plant that forged the F6F Hellcat amid constant air raids was a study in small, human things. It was the story of men and women who taught themselves to listen, who crafted jigs and modified baffles, who argued long into the night about tempering cycles, and then, the next day, stood in line at the mess for stale coffee. They were not mechanical saints. They were, in the best sense, practical moralists, people who measured the world by the dependable hinge of a part and by the life it might protect. When visitors today walk into that museum and study the Hellcat wing, they see metal polished to a dull sheen and panels fitted with quiet precision. A placard explains the plane's role in the Pacific War and the industrial effort behind it. A little handwritten note left by a former worker decades after the machines had cooled says only, "We tried to make it true." The words are elliptical, modest, and, in their plainness, vast. There remain open questions that historians and engineers still debate. The precise chains of causation between a plant's procedural changes and tactical outcomes at sea. The full arc of technological lineage from wartime handcraft to post-war engines and turbines. Those questions are the work of archivists and scholars. Where this narrative has taken care to be specific, it has also left room for verification. Production figures, direct causal claims about strategic outcomes, and certain procedural adoptions mentioned here should be cross-checked with primary sources. Verify. Archival confirmation needed for production attributions, specific procedural adoptions across the Hellcat production network, and any direct technological lineage claims. But for the people who sweat in the bays, the story needed no archivally verified coda. Their truth lived in quieter measures. A plane that returned, a pilot who wrote a short thank you, a part that no longer sang before it failed. Those small outcomes mattered because they were the ones that touched the human lives behind the headlines. The plant's final arc was neither triumphal nor tragic alone. It was braided. The men and women who left their marks on rivets and ribs also carried away the weight of what those planes did. They became, in their different ways, caretakers of a complicated legacy. Some entered industries that remade their skills into peacetime machines. Others tended the stories and the artifacts that would educate later generations. On the museum plaque, below the factual summary, someone placed a clipped reproduction of Brackett's note. Examine transition of stress pattern from pre-rivet to post. Compared to trial 34, consider perforated ribs. It is an odd sentence to memorialize, technical and prosaic, but it speaks to the ethos of the place. Attention to detail, a willingness to try practical fixes, and a respect for the small, iterative labor that underpins large outcomes. If you stand beneath the display and listen to the recorded sound of a test cell, a looped reel that plays the steady, low hum of engines and the occasional keening of an old gauge, you can imagine for a moment the plant at 2:30 a.m., lamps masked, and a distant siren. You can imagine a man like Brackett with a ledger on his knee, and an apprentice like Samuel listening to a rivet song. You can imagine Harold with his pencil-smudged sketches and Lillian touching the locket she would later hang in a museum case. The machines cooled. The sirens quieted. The blackout curtains were drawn back into storage. The world moved on. But the sound, once known, does not entirely leave those who learned it. It becomes a memory that hums in the palm like a small private instrument, an echo of labor, of care, and of the uneasy moral work of making in wartime. If this story resonated with you, if the quiet labor behind big machines caught your imagination, like and subscribe for more inside stories of industry and war.